Hey, welcome back. This is Charlie, and this is the intro video for Lab 2, Earth-Sun Relationships and Day Length. So here for starters is the diagram from the textbook that we've been using, at least in my lecture class, of the different seasons. Let's take a look at the slides. So first thing, I want to show you this animation of the seasons. Okay. Now we've got an animation that's going to be useful in showing us how Earth and the Sun combine to make seasons. So first thing I want to do is go over the 4 reasons that we have seasons, and then I'll take a look at how those combine to make seasons, and then what are the effects of the seasons. So let's start with the 5 reasons we have seasons. I'm only really going to pay attention to 4 because the 5th, it's because Earth is spherical. Because Earth is spherical, for example, on this day, you can see at the equator, they're getting sun at a 90-degree angle. The subsolar point is the equator. And so everybody at the equator is getting sun shining directly on them. As you move away, the angle of the sun moves away from vertical. So if you're 45 degrees away from the subsolar point, the angle of the sun hitting the surface is going to be a 45-degree angle. And then finally at the poles, the sun, the beams from the sun are actually parallel to the ground. So they're just grazing. That's because of sphericity. Because of Earth's spherical shape, different locations get different sun angles on the same day. So let's go through the other 4 reasons that we have seasons. You can see Earth is rotating on its axis. You can see that Earth revolves around the sun once a year. So because Earth is rotating on its axis, we have 24-hour days. It takes 24 hours for Earth to rotate. It could be different. We always see the same side of the moon. As the moon goes around Earth, we only see the same side of the moon. If that was the case, one side of Earth would be baked by the sun and the other would be completely frozen. So we've got revolution, we've got rotation, we've got axial tilt. You notice that the Earth isn't straight up and down. If we move it to June, you can see Earth is tilted 23.5 degrees off of vertical relative to the orbit of Earth around the sun. So relative to its orbit, Earth's axis is always tilted 23.5 degrees. So that's why the tropics are at 23.5 north, 23.5 south. It's because that's Earth's axial tilt. So Earth's axial tilt is 23.5 degrees. The other aspect, it's called axial parallelism. So you can see right now, it looks like the axis is pointing to the upper right. In June, September, the axis is still pointing to the upper right, and in December, it's still pointing to the upper right. In reality, it's pointing at a star that we call the North Star, that's also called Polaris. The name of that star is Polaris. And in 13,000 years, Earth's axis will be pointing in a different direction. We'll talk about that when we get to the chapter on glaciers and climate change. It's important in long-term Earth cycles, but in the short term, it takes 26,000 years to go through a full cycle. So it's not important. It's not important for today. It's incredibly important. Axial precession is incredibly important. So Earth's axis always tilting 23.5 degrees as Earth revolves around the sun. Because of that, in June, you can see the northern hemisphere is tilted towards the sun. So above the Arctic Circle, they have 24 hours of daylight. Below the Antarctic Circle, they have 24 hours of darkness. And every day of the year, the equator has a 12-hour day. And on this diagram, the subsolar point is hitting the Tropic of Capricorn. Anytime the subsolar point is the Tropic of Capricorn, that tells you it's the June solstice. So in summer, the northern hemisphere is tilted towards the sun, so they get more direct sun rays. 3 months later, it's going to be the September equinox. So you can see the axis is still tilted towards the upper right, but if you're looking at it from the sun, the terminator line is running from the pole to the pole. So everybody on Earth has a 12-hour day. On the equinox, the subsolar point is the equator, and everybody has equal hours of day and night. So there's 3 things that go with E. On the equinox, it's at the equator, equal day and night for everybody. Every single day, if you're at the equator, you have 12 hours of daylight, but the poles go from 24 hours of daylight to 24 hours of darkness. So let's see what that looks like 3 months later as Earth keeps moving. 3 months later, now you can see from this angle above the Arctic Circle, you have 24 hours of darkness. And if you are below the Antarctic Circle, you can see the sun never sets. You have 24 hours of daylight. The subsolar point in this case, the direct rays from the sun are hitting the Tropic of Capricorn. And it is the December solstice. 24 hours of darkness, 24 hours of daylight. And then as we move from the December solstice back to the March equinox, we're back to 12 hours of daylight. It's the equinox, the sun is at the equator, the subsolar point is at the equator, and everybody has equal hours of day and night. Okay, this is another animation. I've put a link to this in the intro materials for the lab. It's pretty simple. I really enjoy it though. There's a little person that you can move from the equator to the South Pole, back to the North Pole. I'm just going to put our person about our latitude. So I'm going to try to get them just shy of 40 degrees north. That's good enough. Okay, so it's December, which should tell you it's around the time of the December solstice. You can see the inclination of Earth. You can see that it's dark above the Arctic Circle. You can see it's light above the Antarctic Circle. And here is our person at 40 degrees north. And you can see the angle of the sun hitting the ground. The angle of the sun over the horizon is about 27 degrees. And you can move, very slowly. I think it wants to play as an animation. I'm just going to play with it. So on the equinox, you can see the subsolar point here is at the equator. You can see the angle of the sun above the ground for this person is 51.4 degrees. And as we move from the March equinox to the June solstice, you can see the angle of the sun gets steeper. You can see how the angle of the sun changed. The subsolar point moved from the equator to the Tropic of Cancer. And so the angle of the sun now is 74.3 degrees. As we move towards the September equinox, you can see the subsolar point is moving back to the equator. So now the sun angle is about 50 degrees. And as we move from the September equinox with the subsolar point at the equator, we're moving to the December solstice. And you can see the angle of the sun now, it's only 27 degrees. You can see the subsolar points in the southern hemisphere, 24 hours of daylight, 24 hours of night. I hope you find this useful. I hope it solidifies and makes more concrete the relationship between Earth and the sun. I guess you could play the animation and notice how in this animation, it looks like, and I'm going to stop it because otherwise, it looks like, stop. The sun is, in this case, it's always going to be pointing up to the upper left. So you can see the southern hemisphere is pointed towards the sun, which tells us it's got to be winter in the northern hemisphere, summer in the southern hemisphere. And then 6 months later, you can see now it's sunlight at the North Pole. So it's got to be northern hemisphere summer and southern hemisphere winter. Anyway, that's the animation. It's from the astronomy education program at the University of Nebraska, Lincoln. I hope you enjoy it. I have embedded in the slides and given you a link. It is another animation. This is a YouTube video taking you through the seasons and showing you how the sun angle changes in different locations over the course of a year. I would say watch it as many times as you want. In fact, I would probably recommend watching it before I start this video. I would watch it before I start the notes. I would just start with this video. It's a good video. It'll give you I think once you see Earth and the sun and how they relate to each other throughout the year, once you see the animation, the rest of it will make a lot more sense. So I'd start with that video. This is sphericity. I just wanted to point out the importance of latitude. It's an incredibly important concept. It's like the most important concept in the entire semester. Latitude, 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 latitude. So this is just showing that on this day, the subsolar point, which is the location that the sun would be hitting, the subsolar point is right here at the equator. So they're getting direct rays and the sunlight is very concentrated because it's hitting the surface at a 90-degree angle because the rays of the sun are parallel. as you move away from the subsolar point, they hit at less and less and less of a vertical angle. So at the equator, it'd be hitting at a 90-degree angle. Every degree you move away from the subsolar point, the angles of the sun rays move 1 degree from vertical. So at 45 degrees, the angle hitting the surface would be a 45-degree angle. And as you move farther and farther away from the subsolar point, the sunlight gets more spread out. It is less concentrated, so it's not as strong. I know this is obvious, but this is why the tropics are hot and the poles are cold. It's because Earth is spherical, and so the angle of the sun rays to the ground is different at different latitudes on the same day. Okay, so here we've got the analemma. The analemma is a diagram. You can see there's dates. September, October, November, December, January, February, March, April, May, June, July, August, September, October, November, December. And this is a diagram that'll show you the declination of the sun, which means the latitude of the subsolar point. Or as I think of it, if you wanted to go someplace and get really tan with the sun right over you, all you got to do is look at the analemma. So September 20-ish, around the time of the equinox, the sun is at the equator. Around the time of the solstices, the sun is 23 degrees north or 23 degrees south on the two solstices. So at the equator, on the equinox, at the tropics, at the solstice, at the tropics, at the solstice. So I wanted to point out that the sun moves from 23.5 degrees north to the equator to 23.5 degrees south, back to the equator over the course of a year. So over the course of a year, the angle of the sun is going to change 47 degrees in any one location. So when we talk about seasons, we're talking about two things. Changes in the angle of the sun. We're really going to work on that in the next lab, in lab 3, and changes in the hours and daylight. So one of the key terms, I put it in bold, declination. The sun's declination is the latitude of the subsolar point. The subsolar point is the latitude where the sun is hitting the surface at a 90-degree angle. So the sun's declination is the latitude that's getting sunlight at a 90-degree angle. Seasonality increases with latitude. If you're at the equator, every day is going to be like every other day. As you move away from the equator, the seasonal differences between summer and winter get bigger and bigger and bigger. Seasonal change, so the two things that change with the seasons, day length and the angle of the sun, around the solstices, it's very slow. In fact, around the time of the solstice, day length doesn't change and the angle of the sun doesn't change. But around the time of the equinoxes, the change in day length is a couple minutes. So as we approach the equinox, as we're coming from winter towards summer, we're gaining 2.5 minutes every day. And as we move from fall into winter, we're losing about 2.5 minutes every day. People that play sports in the fall know exactly what I'm talking about. So if you're losing 2.5 minutes a day, in a week, you're making big differences. So if you have practice that's 2 nights a week in the fall, I remember doing soccer, doing baseball. 1 week it's dusk at 8 o'clock and the next week at 8 o'clock it's pitch black. And you think, what the heck? How did that happen? And the reason is it's around the time of the equinox. We'll get to that in the last part of the lab. So here we've got a diagram of Earth with some of the locations of the subsolar point. So on the equinoxes, the subsolar point is at the equator. This is all review. We just looked at this in the videos, but I like to repeat things. So on the June solstice, the subsolar point is the Tropic of Cancer. On the December solstice, the subsolar point is the Tropic of Capricorn. And on both the March and September equinoxes, the subsolar point is the equator. So there are 5 reasons for seasons. We've got revolution. Earth revolves around the sun once every 365 point something days. Rotation. Earth rotates on her axis once in 24 hours. Earth is spherical. Earth's axis is tilted at 23.5 degrees off of its orbit. The northern end points towards Polaris, which is the North Star right now. And axial parallelism. So that's the idea again that as Earth revolves around the sun, the axis points in the same direction. So here this is showing Earth's tilt 23.5 degrees relative to its orbit, also showing the difference between revolution and rotation. Earth rotates on its axis, revolves around the sun. So here we've got Northern Hemisphere summer, Northern Hemisphere winter, and remember the seasons are 6 months apart in the two hemispheres. So in what I'm calling winter here, these are Northern Hemisphere centric seasons. And you'll notice these are the only slides you'll see where I've got them labeled summer and winter. The rest of the time I identify the month because it's clearly summer in the Northern Hemisphere. The Tropic of Cancer is the subsolar point. Below the Antarctic Circle, they have 24 hours of darkness. So it's clearly Southern Hemisphere winter. And by the same token, in June, when it's our summer, the subsolar point, wait a minute, I got backwards. So in December, the subsolar point is now the Tropic of Capricorn. It's winter for us. It's 24 hours of darkness above the Arctic Circle. But at the Antarctic Circle, in what I've called winter, because it's December, they've got 24 hours of light. So in Australia, summertime is in December. So Santa Claus comes in the middle of summer if you're in the Southern Hemisphere. So here we've got another view. This is like a slices of time of the previous diagram, showing going from the June solstice, to the September equinox, to the December solstice, back to the March equinox, showing the combination of those 5 factors that cause seasons, and then showing the side view at the June solstice and the side view at the December solstice. Oh, I love this. So this is a combination of 4 photographs taken by a satellite that's perched over the equator. So they're taking satellite pictures all the time. But from this point of view, you can see that the angle of the terminator line, so March, the terminator line is the line that separates day and night, is running from the North Pole to the South Pole on the equinox. On the September equinox, the terminator line is running from the North Pole to the South Pole. On the solstices, the terminator line is running from the Arctic Circle to the Antarctic Circle. So above one, you've got 24 hours of light, and below the other, you have 24 hours of dark. And then in December, you can see the subsolar point, which is perpendicular to the terminator. So if you drew a line at a 90-degree angle from the center, you'd find the subsolar point is here at the Tropic of Capricorn. And if you're below the Antarctic Circle, you've got 24 hours of daylight. If you're above the Arctic Circle, you've got 24 hours of darkness. And this is an animation of the same thing. It's just a picture. It's a black and white version of what you just saw. It's in the slides. If you click through on the slides, you can watch the animation. It's kind of fun. In fact, some of the things that you can look for are the sunshine, the glint of the sun, and actually see the shifting subsolar point from the equator to the Tropic of Cancer, back to the equator. I'm going to start it again because you really see it. So now we're going from winter to spring as the sun crosses the equator, into summer, Tropic of Cancer, back to fall, back at the equator. I hope you enjoy that on your own. So we have 4 seasons. They are 3 months apart. It goes solstice, equinox, solstice, equinox. We have the December solstice, March equinox, June solstice, September equinox. They alternate. March and September are equinoxes. December and June are solstices. December is when it is our winter. June is when it is our summer. And the dates, just remember the 21st of the month. They change a bit because Earth's orbit around the sun isn't a perfect circle. It's an oval, and it varies a little year by year. But if you just remember the 21st for the date, the December solstice, December 21st, you'd have to look it up on the web to find out when the actual date of the solstices or the equinoxes are, but 21st is close enough for my class. On the solstice, the subsolar point is the Tropic of Capricorn. It's southern hemisphere summer. 3 months later, it's the March equinox, March 21st. Everybody on the planet, 12 hours of daylight. Subsolar point is at the equator. On the equinox, the sun is at the equator. June solstice, June 21st. The subsolar point is now 23.5 degrees north at the Tropic of Cancer. It is summer in the northern hemisphere. And then 3 months later, it's the September equinox, September 21st. The subsolar point is at the equator. Everybody has 12 hours of daylight, 12 hours of night. So everybody has 12 hours of daylight and 12 hours of night. Day length. Day length is the length of the day. Day length varies with latitude. The equator always has 12-hour days. The poles go from 24 hours of daylight to 24 hours of darkness over the course of a year. So latitude varies, so day length varies with latitude. Day length varies with the seasons. Summer has longer days, winter has shorter days. So two aspects of day length. Day length is controlled by the combination of what time of the year it is and what's your latitude. The change in day length, because we live at 40 degrees north, there's about 6 hours difference between the longest day in the summer and the shortest day in the winter. So we have about a 15-hour day in the summer and about a 9-hour day in the winter. So we have about a 6-hour difference. So around the time of the solstice, in fact, the word solstice means the sun has stopped, and it doesn't mean that it's stopped in the sky. It means that it's not changing. The day length around the time of the solstice, the day is the same length, and the angle of the sun doesn't really change a whole lot day to day. At the equinoxes, we've got super rapid change. Like I mentioned, we have about 2.5 minutes change in day length around the time of the equinoxes. The fall equinox, we're losing 2.5 minutes, so that's what's happening right now. And then in the spring, we're gaining about 2.5 minutes of daylight every day. And same thing, the angle of the sun changes rapidly around the time of the equinoxes, and the angle of the sun doesn't really change around the time of the solstices. For your lab, we're going to look up day length using this web page. That's going to be the easiest way to do it, but in case you're having issues with the web page, I will print out that web page and supply you with PDF versions of the tables from this so that you can look up the data yourself. So if we go to time and date, I love this website. In fact, you're going to have to start tracking, many of you are going to have to start tracking changes in day length. So there's this graph over the course of a year. You can see in the summertime, the lightest blue is daylight. The darkest blue is nighttime. And then in between, there's 3 types of twilight. There's civil twilight, nautical twilight, astronomical twilight. Civil twilight, the sun is just set. It's still light enough that legally you don't need to use headlights. Nautical twilight, it's getting darker. And finally, astronomical twilight, it's not completely dark, but you can see stars. So around the time of the summer solstice, June 21st, you can see that day length for us is, it's right down here, day length is 14 hours and 51 minutes on the longest day of the year. And on the shortest day of the year, December 21st, the shortest day of the year, we get 9.5 hours of daylight. So that's part of it. And the other part, if we go down now, so this is, I programmed that length to take us to June. You can see June, the solstice is right in here. It's got the sunrise, sunset, day length, and then what the difference from today to tomorrow. So on the longest day of the year, it looks like a 14-hour and 51-minute day. And the change is you lost a second, 4 seconds. And you can see the change in time is accelerating as you move away from, in this case, the solstice. So if we look at the other solstice, we can go to December. This will be a preview. So if we go to December, now around the 21st, it's going to be the shortest day. You can see the sun comes up at 7:18, sets at 4:46. For a 9-hour and 28-minute day, we're losing 1 second. All right, that's not super exciting. Let's take a look at March. So in March, and one of the things I should probably tell you, I also set this link up so that it's taking us to right about our latitude and longitude, so it'll be accurate. You can set, in fact, part of your assignment will be setting in different values or going to different lengths and then letting me know, telling me what the sunrise and sunset times are for those places. So in March 21st, sun comes up at 7:04, sets at 7:17 for about a 12-hour day, but every day we're gaining 2 minutes and 30 seconds, 2 minutes and 30 seconds. So around the time of the equinox, we're gaining 2 minutes and 30 seconds. Around the time of the September equinox, you can see another 12-hour, 10-minute day. Oh, right. That extra 10 minutes, that's because of the refraction of the rays of the sun as they pass through the atmosphere. As light from the sun hits Earth's atmosphere, it gets bent. And so we actually get about 8 minutes more daylight every day because the rays of the sun are getting bent by the atmosphere. But you don't need to worry about that for now. You can see every day on the 21st. Oh, in fact, as of September 1st, we're going to be losing 2 minutes and 23 seconds. By the time we get to the solstice, or the equinox rather, we'll be losing 2 minutes and 28 seconds. And then, let's see, that's the same. Let's go to October. And hopefully you can see that the change in day length is coming down. 227, 216, 211. And then as we get back to December, 1 minute, 20 seconds, 1 second. And then after the winter solstice, the sun returns and the days get longer. That's it for this lab. I hope you enjoy it.